Just to give you a little bit of information on who we are, my name is Kendall Dyman, and in addition to being a student here at Lipscomb, I work in Atlanta. And my colleague is Gabriel Bassett, who is a senior information security data scientist at a Fortune 100 company, and also the owner of Information Security Analytics LLC. So today, we're going to go through this presentation. I'll start with a brief introduction and kind of tell you how we came to this project and the landscape that it sits in. Talk about how we generated some synthetic medical data. Show you the Bassett-Dyman training algorithm and the query algorithm. Give you a view of the user interface, and if all goes well, a live demonstration. But we'll keep our fingers crossed for that one. Talk a little bit about the future work and the things that we want to do in continuing this project, and then conclude. So, medical diagnosis is something that's going to happen all the time. If you are sick, you go see a doctor. If you can't see a doctor, you see a nurse. If you don't have access to a medical practitioner, you're probably going to have to figure out what's wrong with yourself in order to find out what to do to treat it. But if you want to be qualified to provide medical diagnosis, it takes a lot of school to do that. So we have a small subset of people who are qualified to do it, yet it's something that we all need at some point, and it's a huge need in our society. So we're collecting all of this medical data, and the government has also mandated that in our collections we need to be able to show a way to use it meaningfully, to realize its true potential and improve the safety, quality, and efficiency of care. So one of the things that we can do to improve quality and efficiency is provide quality medical decision support, which is not only going to improve the quality of care, but improve the quality of lives of the people who benefit from it. And there are a lot of people who can benefit from quality decision support. So we have been working on decision support for decades. Initially, the systems looked like warnings, reminders, and suggestions. So they're a set of if-then rules. If A happens, then do B. If a test comes back and gives you this result, then this is how you need to treat it. But really what this comes down to is just a set of best practices that are put into an algorithm and says, here's what you need to do in this scenario. But it doesn't learn and work with the data that you give it to get better. So some people have worked on systems that are a little bit smarter. A lot of times those systems are very specific sets of diagnoses that they cover. So there may be heart disease systems that look at, if you have these symptoms, this is what type of heart disease you may be dealing with. But Gabe and I have talked about how differential diagnosis works. So when you go to your doctor, they get an idea of what's going on with you and what's wrong. And then they use the things that you've told them to rule out possible diagnoses as well as to get a list of probable ones. So this is not magic. The doctor does not just look at you and say, I know exactly what's wrong with you. They have to go through a logical process. So if it's logical, Gabe and I think that a computer ought to be able to do it. So that's how we came to this model, which I'm going to give you a few definitions here because I'm going to use these words a lot and I want you to know exactly what I mean by them. A diagnosis is going to be an identification of an illness or another problem. A sign is going to be objective evidence of a diagnosis, so something that you can measure, something that you know, I'm female, so that's going to mean that there are some things that can be wrong with me that are not wrong with a male. And then symptoms are subjective evidence of a diagnosis. So I can tell you that I feel really cold all the time, and that's not something that you can necessarily measure. So the way this model works is it's going to look at signs and symptoms and their relationships to diagnoses. It's also going to look at tests and treatments. So you have every sign and symptom and all the diagnoses it's connected to, as well as the treatments that go with each of these signs, symptoms, and diagnoses. And then out here, we've got possible tests. And the tests are going to be pointed toward the signs only, but everything else is kind of interrelated. We'll go into a little bit more detail on how all of these things come together in this model. But in order to build this model, what you need is medical data. We didn't have access to any of that, so the first thing we had to do was create some ourselves. So step one of that is to generate a set of truth data, just ground truth. If you have this diagnosis goes with these signs and these symptoms. So the first thing we did was to set a static value, which meant we had to determine how many signs do we need, how many symptoms do we need. We had to determine how many of those signs and symptoms would be true and look at how they were distributed. then take some signs and symptoms and attach them to actual diagnoses. Because once you've determined that some signs are going to be on a continuous distribution where it's such as an age, or you've got a discrete distribution where it's a 1 to 10, what's your pain level, or a yes, no, or a maybe, or just a binary yes or no, someone exhibits this. And then you pick the signs and symptoms for each diagnosis, and you have to decide how those are distributed with the diagnosis. So that's the perfect world set of data, but as you can imagine, medical records are not going to look like that. So step 2 of our synthetic data was to generate the records that we used to train the model, which had to have a little bit more noise in them. So to generate these records, we chose a diagnosis, we picked a number of signs and symptoms to go with it, and then for each sign or symptom we have to determine is it true or false, because you can absolutely have a false sign or symptom to go with your diagnosis, and that can happen in medical records. There may be signs or symptoms that get misreported, not noticed because they weren't brought up or weren't tested for. And so you have to decide if the sign or symptom is true or false, and then if the value is true or false. So I can tell you that the pain level is a 7, but is that correct? So this set of data is what we use to train the records and will hopefully mirror what the real world records would look like, so that this system is actually tested against something that works like the real world. So once you have those medical records, here's how the algorithm works. You take all the medical records and put them into the model, and it's going to create a graph. It's going to map every sign to every diagnosis that it's mapped to, and every symptom to every diagnosis that it's mapped to. So you'll see here you have lots of lines in between each symptom and all the diagnoses. Symptoms are going to occur multiple times, signs are going to occur multiple times out of diagnoses. So in this intermediary graph, you've kind of taken everything and separated it out and gotten it a little bit prettier. In step 2 here, on the far right, you'll see that you take all those signs and symptoms and aggregate them. So each sign or symptom is now only going to have one node in the graph. And on the edge between the sign or symptom and the diagnosis, you're going to store a probability score as well as the number of times that sign or symptom was actually linked to that diagnosis. So that's going to tell you how likely it is that sign or symptom goes with the diagnosis, and also how many times it literally appeared connected to it. So if that was a low number, it's going to be stored on there. If that was a high number, it's going to be stored on there, but you're going to know for each one. You can also go back to this to check it at some point if you needed to know how we came to what we came to in the end of the model. So once you've got the model, you feed your signs and symptoms in. So when you come to your doctor and say, here's what's wrong with me, and then your doctor does the tests, he has all the signs and symptoms he needs. And what the model is going to do is look at each sign and symptom and identify all possible diagnoses in the graph. And it's going to take all of those, and if the model has an edge from the sign or symptom to the diagnosis, it's going to look at the probability function. It's going to determine what the likelihood is on that edge that this diagnosis belongs with this sign or symptom. It's going to weight signs higher than symptoms because signs are objective instead of subjective, so there's a little bit of weight given to a sign over a symptom. It's going to weight a value by the number of times the sign or symptom has been seen attached to the diagnosis, so that number that I talked about will also give some weight to it. And there's a potential to weight the value that a subject matter expert gives. So if a physician knows that something is more important or wants to check and see with something, one of your signs or symptoms being more important than the others, you can weight that. So once it's found all of the possible diagnoses, it takes them and gives them a score. It's going to sum all of those values that it's looked at and give them a score, and then rank them in order from most likely to least likely. And it gives you just a clean list. So behind the scenes, that's what you're seeing. But in real life, it looks a lot more simple, and Gabe's going to give us a live demonstration.
Sure, and with all live demonstrations, say it for they don't always do what they're supposed to do, but we'll give it a shot. And so this is the interface, and it's the same one you saw in the last chart. It's basic. The underlying system's a Python system built, and the interface is JavaScript and HTML, the same kind of stuff any website would produces. However, it's able to interface with the model on the back end. Now, earlier today, I built the model, did the steps we talked about, took 900,000 training records, sent them in, built that intermediary graph with each sign and symptom and diagnosis in there once, and then multiple relationships between them, and then turned it into the final model, which has a single node for each diagnosis, a single node for each sign and symptom, but then a probability distribution on the edge between them, so that, like we said, if the data was binary, male versus female, there's a probability distribution in there, and even though some of the times it's going to get listed incorrectly, we can pull out and put whatever value we get in from the test record into that and pull its place on the probability distribution. This is why I keep asking about probability distributions. It's become very relevant in my interest. So, okay, so what we did is generated a new diagnosis. This is a medical chart. Now, the medical chart, of course, wouldn't have the diagnosis line on it. That's just so we know what the true one would be. In reality, it would have a few signs, a few symptoms, and values for them. And these are all numeric, but you can see those being true or false. A pain, even something like pain, is going to be, like you said, what's your pain on a scale from 1 to 10? And by the way, I actually know this record comes out correct if I diagnose it. So we're going to this will cooperate. We're going to try something completely different. And this record is brand new. When I click the button, it generated a completely new one. This is completely new data. I have no clue whether this is going to work or not. And so I'm going to go and copy the signs and symptoms over into the model. And I think I needed, 3 signs, 3 symptoms? 3, 6. So value 1. So this takes a second. I probably should have been doing it while I was talking. We're going to copy over all the signs and symptoms. And right now you have to do it exact. If we were to go and actually produce this, of course, we would go make it so that it auto-completed for you. You didn't have to get things exact. We could use a little bit of fuzzy logic, 11th time distances and stuff, and such to kind of complete the text or figure out what you meant. And in here where it says sign 2208 or symptom 142, really you'd be looking at something out of ICD-10, where it's got an actual value, an actual name. These are just our placeholder names and numbers that are synthetically generated. But in reality, it can come from, it can be any string. It's not specific to this kind of nomenclature. So copy over the last 2, let's see what was the value, 0.9. Sorry, you get fewer signs and symptoms sometimes you get more. Honestly, I don't know which of these are actual signs and symptoms of this diagnosis and which are not. I am going to copy them over whether they're the correct thing or not. And we're going to copy them in. And this is as if a doctor had put in these values in, or when they took your vitals coming in as the nurse, they took information about you, they asked for your symptoms, they put in your values, and it all went into the EMR. And so this is like the data going into the EMR. And on the back end, it goes and runs the model and comes up with a potential diagnosis. And it says the most likely diagnosis is 525. Let's see if we're right. And we are. By the way, I was so worried because every time we run this, it's got it right, which is not supposed to happen. This thing is probabilistically right a lot of the time, but it is not always right. And so I was worried that this would be the one time, like on camera, where it wouldn't actually get it right. And so that's the model actually working. You can tell from the interface that there's nothing special about this. In fact, the first time I ran this, I ran it on an iPad. There's no reason it couldn't be run on a phone. It doesn't take a lot of, it's not a heavy client. So I'll pass it back to you. It worked this time, but Kendall's going to talk a little bit more about how often it works right when you run it a whole bunch of times.
The reason we're always nervous is because we know how accurate it is, and so it's not always going to give us the correct answer. Before I move on to talk about the results, I will say that one of the things that we are excited about here is that this just runs on an internet connection on a really simple web interface. So it doesn't require a lot of training to use, and it doesn't require you to purchase a brand new system or a piece of hardware. So this makes it a really accessible tool to get to anybody who has an internet connection and a device. So your doctor can use this on a phone or tablet, as Gabe talked about. And as you saw, it's fairly easy to do. So we tested a lot of different numbers of training records. Gabe generated millions and millions of records and kept generating new ones and testing this model with more and less. And what we saw was that 800,000 records, which is what you see right here, this spike, is where this becomes pretty much completely trained. It doesn't get much better as you add more records in. So 800,000 is going to be a good point for us. And if you think about 800,000 records, that's a lot of data. That's a lot of knowledge, and a single doctor cannot see 800,000 patients in his or her lifetime. So 800,000 records is a lot of information aggregated in one place from a lot of smart people. And at 800,000 records, we see that the result returned and the top spot is correct, the correct diagnosis 65% of the time. 85% of the time it's going to be in the top 5, and 91 to 94% of the time it'll be in the top 20. So when you use the system, the diagnoses that you're going to get back, it's highly, highly likely that one of the first things you're going to see on that list is the true and correct diagnosis. So just to kind of give you another picture of that, what you're looking at here, I'm going to focus on this chart because this is the 800,000 training records. Along the bottom here is where the correct diagnosis falls in the list, and this is the number of times that the diagnosis falls in that spot. So you'll see that this is 100, and the majority of the time the correct diagnosis falls in this under 100 bucket. We wanted to look at that closer and see that, well, in the top 100 is great. That means that you're closer to knowing what's wrong with someone than you were before, but it'd be nice to be closer. So this slide is going to zoom in a little bit more. This is the 800,000 training records. This is how it changes based on the number of training records. So what you see across the top is the number of training records. So this is the same 800,000 that we were looking at before. You can see that it only goes up to 60. So this is the top 60 diagnoses. The majority of the time, the correct diagnosis is in the top 10. So what does that mean? Well, it means that this system is not going to tell you exactly what's wrong with you. You still need a medical professional to give some input. It's not going to replace your doctor, and it's not going to give you a definitive diagnosis. But what it can do is help the people who are making those diagnoses. So it's going to be able to narrow down what could be wrong with you. If it's something that your doctor has never seen before, it's going to give them a place to start looking. Or if they're just baffled, maybe it'll narrow it down for them. And what is in test but not in production right now is that eventually it will suggest, based on these top-end diagnoses, here are some tests you could do to rule some others out. And here are some possible treatments that will treat the top 5 that won't hurt the patient. So you have a moment to say, I don't know what's wrong with you definitively yet, but here's something I can do now that's not going to hurt you, and if it's one of these things that's deadly, it will help you. And it should also be able to recommend tests to differentiate between the top number of diagnoses that you're looking at. So when you know that it's likely one of these top 20, here's a test that could rule out 10 of them, or a test that could confirm that it's one of these 10. We're also hopeful that someday this could be used for a more automated process. So, you know, when something is wrong and you go to see a doctor, if the nurse or whoever you see when you first get to the doctor's office is able to put your signs and symptoms into this model before your doctor ever gets to you, then the doctor's going to have a list of possible things to look for when they get in the office. So it's going to speed up your care. And then as wearables are becoming more common, Apple just released a watch. A lot of people are wearing Fitbits and other fitness trackers. As those things are monitoring your data, there's a potential that someday a system like this can have that data fed into it. And then if there's something concerning, if your heart rate and your temperature start to do something that leads the model to think that they're doing something wrong with you, then an alert can be generated to say, perhaps you should go to the doctor and maybe have this checked out. And as I mentioned earlier, 800,000 records is a lot of knowledge. So this is going to be a lot of doctors from a lot of different schools, and it's not going to be limited to this one person and the amount of things that they've seen or learned over their lifetime. They're going to have the benefit of years and years of experience. And 800,000 records, if you're a company like HCA, that may be gathered very quickly. And some places you're going to have to gather data for weeks. But if you have a lot of medical records, you have a lot of backing to the system. So there's a lot left to be done. There are a lot of things we'd like to change in the future. For instance, the test and treatment notes, which, as I mentioned, we have worked on but are not yet ready for production. And we'd like to try with actual medical records. We're pretty confident that it's going to work as it does with our synthetic data, but we want to see that happen. We'd like to be able to mark signs and symptoms required so that you can filter data. So please only return the diagnoses that are attached to this sign or symptom that I, as a subject matter expert, deem important. And that would be something that you could turn on and off so that the doctor can say, you know, I want this rash that this person has is more concerning to me than some of these other symptoms that they're showing. So make sure that all the diagnoses that come back are attached to this sign or symptom. Gabe mentioned that we'd like eventually to be aligned with ICD-10 so that, you know, the autofill will happen and that the doctor will be led to know what to look for as opposed to having to type things in verbatim. We'd also like to have a more robust distribution for the sign symptom value sets and matching, and a better filtering system for the sign symptom to diagnosis relationship. So those signs or symptoms that aren't really very connected, they occasionally show up in the diagnosis. The more of those you can get out, the more optimized the system will be. To kind of wrap it up, this is exciting to us because it's going to give doctors all over the world expertise in all diagnoses, essentially, that have ever been given. It's going to make it easy for them to get to it. And you're going to have your experienced practitioners who may just be able to use this for something that's odd or unusual, or just to kind of speed up their work. But then especially in an unexperienced or under-resourced area, you're going to be able to provide this technology to a doctor or just the person who's been designated the doctor in an area where they don't have one, who has very limited medical training and knowledge, and it's going to give them a place to start from. So instead of having all the possible diagnoses in the world to start from, they've got a short list, maybe the top 20, to look at and determine if any of these can be pulled out or if this is what's wrong with the person. So I think most important to us is that there are places that could benefit from this that don't have quality medical care that's accessible. So hopefully this could improve efficiency and quality, as I talked about at the beginning, in those places. So at this point, we'll be happy to take any of your questions.
I'm curious how, so in the example that you showed, you had 3 signs and 3 symptoms that were put in the model. I'm curious if you looked at how the model performs based on, you know, so if you put in 2 signs and 2 symptoms, or 3 signs and 1 symptom, or, you know, those combinations.
So the fact that we got 3 signs and 3 symptoms was purely random. Some of these come up with 1 sign and 4 symptoms. Some come up with 2 and 3, 5 and 1. It actually goes to a distribution and pick the number of signs and symptoms to attach to each. And so we've never tested to see how well it does against them. It should do more poorly against symptoms, because this is the interesting thing. If you go back to the bar charts, zoomed in one. So when you look at this, right, it's easy to say, hey, the model's just getting it wrong, you know, whatever percentage of the time, 5% of the time, that's on the top 20. But in reality, the data is so messy. The signs and symptoms, the signs are 8% wrong, and then even if it has a correct sign, the value is 8% is wrong 8% of the time. Symptoms are 20%. 20% of the symptoms are completely random. 20% of the values for the symptoms are completely wrong. And so, you know, more than likely, the times where it's way off are because it's just got completely wrong data. You know, there's got to be, when you run this, you know, 1 million times, you know, some percentage of those, you know, none of those signs and symptoms are going to be correct. So I suspected it would do, probabilistically over a large distribution, it would do worse for signs and symptoms if you have more symptoms and signs, just because of how we weighted the accuracy, but in reality it does well kind of no matter what it gets.
But you, just to follow up, so you gave examples of where you put 6, combination of 6, but you're saying that if you have one sign and one symptom, that few number, I mean, I'm just wondering if you built in some parameters to say that we have to have X number of inputs, whether it be a combination of the two or something, before we can really.
We could, so it's definitely something we could do. I suspect that, that's something we didn't build in and we also didn't talk about, is kind of the temporal nature of this, right? The person comes in and really, probably when they come in the door, you probably have 4 or 5 symptoms and maybe 1 or 2 signs. Age, gender would be signs, but the symptoms are, I've got a headache and I feel hot and my pain is a 7 on a scale of 10, which you may or may not be able to rely on. Then over time you add signs. And it's probably worthwhile, given its ability to say, look, we're not really sure, but hey, here's what you can do to just treat the top everything. It'd be better to do that, and then as you get more signs, it goes, okay, well, we've got a better idea what it is. And we reshuffled, and here are the treatments now. And it's, that way, care progresses and gets continuously more accurate as you get more data. As opposed to just saying, look, I refuse to look at this just because you haven't collected a whole lot. Any other questions?
Yeah, so what about outliers? So you have something like Ebola that comes about, and it's fairly new, and say it's on the verge of becoming endemic. So the system initially doesn't have knowledge of this particular, the symptoms related to some diagnosis. So I assume you've got to have enough data to be able to surface these things. So what about data on the edge, right?
So you've got 2 options, and really when we did this, we preferentially attached signs and symptoms. So knowing that some diagnoses are really rare, so there's some diagnosis in the training data that just appear very rarely, if at all. Now, of course, when I go and run this one time, I'm also just as likely to not get a rare diagnosis. That is in the model, and that is represented in these larger distributions. However, if you add something like this, because our model is intermediary, it's not a neural net where you don't know what the internal and intermediary steps are, you can literally just go hand code it. If I know what the relationship is between some sign and some symptom, if someone's done all the testing to say, here's what this function is, probability function is, I can hand jam that in there. So I don't have to train it if I have hard. In fact, that was our original idea, was just hand jam all the relationships, and we found it was maybe easier to just train it on actual data. But it's always an option to go hand jam stuff in.
So, and another thought I had about the outcomes. So you're in the top, let's say, if you look at the top 20, you're getting at 94%, something like that.
By the way, this was on 800 symptoms. The test we ran is on 900. We never ran the 900 run of the large runs, but I suspect that it actually peaks around 900, so it gets a little better than the numbers.
So for the diagnosis, I wonder if you, instead of treating the diagnosis as separate, you actually looked at families of diagnoses, because there are some that have a relation, and you actually looked at its ability to classify into family groups. You probably have a much higher, I would assume, accuracy. So you know that, you may not know what, I don't know, what kind of cancer it is, but you know that this is some, it's a high probability of being some type of cancer. And then within that, you have an idea of the individual.
Yeah, and you're absolutely right. One of the things that we did address was either hierarchical diagnoses or hierarchical signs and symptoms, like what's your pain threshold? Oh, it's a 10. What's your pain threshold in your knee? Right. That said, like if you train the model correctly, you could simply say when you got a record in that had values A, B, C, and D, and a diagnosis of some subset of a cancer, you could say, don't just connect those signs and symptoms to that subset, also connect it to the greater parent. That way, even when you got other sub-classifications, you still got that parent. And what that would cause is when the model goes and runs, you're likely to get both the category, which may or may not be right, but you're much more likely to also get the major category. And so, your top 2 or 3 diagnoses might be 3 or 4 of the sub-classifications, but also the major classification, in which case you have what you said, we're very confident it's this major one, now we're just working on the subs.
And then that relates to if you extend it to treatment, right? So
Yeah.
all of a sudden you have a stronger mechanism to point towards treatments because they're probably going to be similar for different.
Exactly. And
If
that's,
it's 3 kinds of cancer at the top, you'll know that
Yeah.
we need to look at cancer treatments as opposed to just whatever treatment.
Exactly.
yeah. And, talking, so this is based off of a lot of discussion with doctors, and the way they've said they treat, right, is, in fact, we've seen this in person, is they don't go in and say, okay, well, they're not engineers. They don't go and try to find root cause and spend, days or weeks or months doing that and then treat that. They start treating everything they could potentially treat in the very beginning. And they'll throw anything at it because their job is to keep the patient alive. It's not to solve the problem. And so that's one of the ways where you can do this, where you had that overarching classification. You treat all the different, you're sure it's cancer, given the signs and symptoms, so you treat all the potential cancers. And this can tell you, hey, these treatments are great, they'll treat all the top things, and by the way, they don't hurt any of the top 1,000. You can be comfortable starting these treatments immediately as you're working to refine your diagnosis. And then as you get it better, you discontinue some treatments, or maybe you refine treatments you have. So that's the real benefit, that's the real strength of the treatments and the testing, is that it lets you make decisions. This is one of the things that really surprises me about this model, is it lets you make decisions without knowing the honest ground truth. And I'm sure this is the kind of thing that drives engineers crazy, because engineers want to find, I'm an IT person, I like to find root cause, but in reality that doesn't always happen in medicine. And this is able to go and figure out what to do without having root cause. Now, you can see where that'd be beneficial, like with, so like you talked about, there's so many people that have whatever level of treatment or diagnosis that's immediately available. Diagnosis is something that happens whether the smartest person in the room is a doctor, a nurse, or the guy with CPR training that just happened to stop on the side of the road. And whether the reason the level of experience is because of that, or because you've got like you talked about, a physician's assistant who's being relied on, even though he doesn't have as much experience as a full-time physician, or it's a little place in the middle of nowhere, a little small town that's got its local doctor that's only seen the things that have appeared in that area, or even the diagnosis is simply something that occurs on the West Coast and is just showing up on the East Coast. This aggregates that entire body of knowledge. And even for doctors that know what to look for, doctors are told that when you hear who's, don't think zebra, right? They are taught, expect the most common things. And even when they get one of these diagnoses that's it's a little off, it just doesn't feel right. They can tell, they can feel that it's not right, but they don't have any, they're trained not to go find those other things. And so this gives them the option, goes and suggests it for them. So when they're getting that, they got the spidey sense going, that there's something not quite right. They can go and look at those top 5 or 10 or 20 and just browse through them. Maybe we link them to a description of what it is. They click on it and they go, that's it. It cues something up from their memory, or they realize that it fits the signs and symptoms they've seen. And they're able to find those outlier diagnoses. So like you talked about, this helps those outlier diagnoses, in fact, especially not just by being able to capture the broader body of knowledge, but also by being able to suggest them to doctors that may even be aware of them. So, any other questions? No? Thank you all for...
Hold on. Oh. Okay.
I've heard this talk many times.
Okay. Well, one last question before we finish. What's the next thing this is gonna be over now for the class. What's the next thing you're gonna do right after you finish this class about this project?
About this project?
Yeah.
Well, I think we probably most like to complete testing, the test and treatment code, so that those recommendations are in there, as well as put in that little checkbox. Because, look, when one of the signs and symptoms is male, you really don't need to be looking at the diagnosis that, it says they're male, but maybe we'll just assume that maybe they're not, just on the off chance. You want to say, look, just give me the stuff that's all for males and females. So we'd like to add that in there. But really, what would be nice would be to partner with one of the hospitals or hospital chains here in town and get some real medical data in here and see can it really do what we think it can do? And if it can we put it to use helping people? Because that's ultimately what this is about, is getting the opportunity to use this to help people. And so along those lines, we plan on publishing this video online. We plan on putting the paper up. And we plan on putting the code up and making it, licensing it for non-commercial use for free. And so that'll hopefully be done by the end of the weekend, and then it'll be available for everyone to use.
Any other questions?
Well, I would just say you guys have done a great job. I really like it. And to me, and I know this is where your head is, Gabe, and Kendall, you've been kind of pulled into this awful IT world that we come from. But this is exactly what we do in IT, right, with problem resolution. So you could take that kind of model that's focused on health, very easily apply it to InfoSec, of course, right?
So
but very easily apply it towards, someone calls in the help desk and they've got a problem, and you come up with, a probability of what might be the case.
Yeah, and that's actually a subtle thing that we mentioned in the paper is, so the CIA has something they published called analysis of alternatives, or analysis of alternative hypotheses, I think. And the idea is that you have different pieces of data which lead you to believe certain things, and where do you need to go to collect more data to strengthen your position. And really, this is, at a broader scale, we're using it for medical diagnosis. Like you said, it's useful any place where you have to choose between competing hypotheses.